In this video, I want to take a look at some theorems that tell us some things about the dimension of a vector space. I'm going to start by just recalling two theorems that were in the previous video. I'm recalling them here just because of their usefulness in so many things here. In particular, if V is a finite dimensional vector space and I have a basis, V1, V2 up to Vn, then I know that any set of vectors in V that has more than n elements must be linearly dependent. And I know that any set of vectors with fewer than n elements doesn't span V. Now, all I've used that theorem for so far is to prove that all bases have the same number of elements. But this is particularly nice when you're trying to decide, I got a set of vectors, is it linearly dependent? Do they span, right? For instance, if you're in R2 and you've got a set of three vectors, are they linearly dependent or independent? I mean, I don't even have to set up the equation k1v1 plus k2v2 plus k3v3 equals 0 and see if I can find some solutions. I know R2 is two-dimensional and I got a set of three vectors. I've got more vectors than the dimension, so that set must be dependent. Likewise, if I'm trying to span R4 and I've got three vectors that I'm trying to use, it's like, it's not going to work. Because in R4, a four-dimensional vector space, any set with fewer than four vectors doesn't span the whole space. Okay, so this is a very useful theorem when just trying to decide, not do I have a basis or not, but just either part of it. Does the set span? Is the set linearly independent? And I know why. I know which part goes wrong if it's not a basis. The plus-minus theorem is also a very useful one because this allows us to add vectors to linearly independent sets to create another linearly independent set. Likewise, it allows us to take vectors, it also allows us to take vectors out of sets that are not linearly independent and do it in a way that doesn't change the span of the result. So, those were from the last video. Now here's a new one. If V is an n-dimensional vector space, and S is a set of vectors in V with exactly n vectors, then S is a basis for V if either S spans V or S is linearly independent. Right? To be a basis, you need to do both. You need to span the whole space and you need to be linearly independent. But this is saying, if I already have some information, that if I know I'm in an n-dimensional vector space and I've got a set of n vectors, right? If I'm in R4 and I've got a set of four vectors, I don't need to show both spanning and independence. I can just show one of them and the other one is guaranteed. In a few videos back when I first started talking about basis, I think, I did an example in R3, and it came down to solving two systems of equations, one homogeneous to show independence and one non-homogeneous to showing span. And it really boiled down to the same question. There was a particular matrix that showed up and says, is this matrix invertible? If it is, then both things were implied, both independence and spanning of the whole space were implied. And this is really the same theorem here. It's just not just in R3, but in a general vector space, in a general n-dimensional vector space. Right? So here's my proof. Right? There's two parts to this proof because I have to essentially show if S spans V, then it's independent. And if I have to show that if S is linearly independent, then it spans V. Because to be a basis, you need both. So if I have one, I got to prove the other. So let's start with, suppose S contains n vector and the span of S is all of V. So if S is not a basis, then it's because it's not linearly dependent. Sorry, it's not linearly independent. So I want to show that it is linearly independent. And I do this by essentially proof by contradiction. I really like proof by contradiction. You essentially assume the opposite of what you're trying to prove and show that that leads to something that cannot possibly be true. So the thing that you assumed cannot possibly be true. It must be the opposite. Right? So I'm trying to show that this set, it spans, so I'm trying to show that this set is linearly independent. So suppose it's not. If it's not linearly independent, then there's some vector in it, in S, that's a linear combination of the others. Throw it away. That doesn't change the span. The span was already V, and so throwing away that one vector that depends on the other ones in S by the plus-minus theorem, the minus part of it, allows us to get a new set that has the same span as the old set, but doesn't have that one particular vector in it. However, this now becomes a problem. This is a contradiction because we know, sorry, now we have a set with fewer than n elements that spans V. But from the first theorem I have up above, right, if it's n-dimensional, any set with fewer than n doesn't span. So this can't be. So S must have been independent to start with. Likewise, let's suppose that S contains n elements and is linearly independent. Now I want to show that it spans. And I'll do that by, if it doesn't span, what happens, right? If S does not span, then there must be a vector in V that's not in the span of S. That's what it means to not span the space. There's something else you miss, right? So I can take that particular vector V and stick it into S, and it'll still be linearly independent, right? S was linearly independent to start with, and now if I add that vector V to it, that's the plus part of the plus-minus theorem, I'll still have a linearly independent set. But that set now has n plus 1 things in it. And I know from that first theorem up above that anything with more than n vectors must be linearly dependent, but the plus-minus theorem said it must be independent. So there's a contradiction here, and my assumption that S does not span is false. So S does span V, and so it's got to be a basis. Either way, one condition implies the other because you know the dimension of the vector space. If I didn't know the dimension, that wouldn't necessarily be true. Next. Oh yeah, this is kind of a fun one. Let S be a finite set of vectors in a finite dimensional vector space. If S spans V, but is not a basis, then it can be reduced to a basis by removing appropriate vectors from S. Likewise, if S is a linearly independent set but is not a basis, then S can be enlarged to be a basis by adding appropriate vectors. All right. This really comes down to the plus or minus theorem. Look at the first part. Right. If S spans V but is not a basis, that means it must not be linearly independent, right? Because if it was linearly independent and it spans, it would be a basis. And so we know it spans, so it must not be independent. So there must be something in S that we can throw away. So throw it away. The span will still be the same from the plus-minus theorem. And then you say, well, is this new thing a basis? Well, if it's not a basis, it has the same span it did before, so it still spans all of V, and so it must be linearly dependent still. So there must be another element in there that's a linear combination of the others. Throw it away. It doesn't change the span by the plus-minus theorem. Right? And so you keep doing this until when, right? Well, the thing is, S was given as a finite set of vectors. So eventually, you're going to get down to one vector, and one vector, if it's the zero vector, I think we ran into this before. If it's the zero vector, you should have thrown it away long ago, right? So if you get down to one vector and it's not the zero vector, then it's linearly independent. So at some point in this process, you're going to have a spanning set that's linearly independent. And that's what a basis is. So if you start with a big set, you can whittle it down to a smaller set. If you started off spanning the whole space, you'll still be spanning the space, and now you've got independence as well, and you have a basis. Okay. For number 2, you're going to start with essentially a smaller set that is independent, and you want to build it up to a basis. Well, if your smaller set is linearly independent, well, if it spans all of V, then it's a basis, and you don't have to do anything. If it doesn't span all of V, there's something out there that's not in this set in the span of this set, then you can throw that into the set and still have independence. Now you have a bigger span because you include that other thing and all of its combinations, right? Are you a basis at that point? Well, if not, you're still independent, so it's because you still don't span V. So there's something else in V that's not in the span of what you've got. Throw that in and keep going. How do you know this is going to stop, right? How do you know this process is going to stop at some point? Well, V is given as finite dimensional, right? There is a finite basis for it. And as soon as you get up to that size, and it may be, you may have started with 2 vectors and this is an infinite, not an infinite, a million dimensional space, right? That's still finite. And you may have to add a lot of vectors in there, but eventually it will stop. And you get up to having n vectors, whatever the dimension of V is, and then you must have a basis. So you can build independent sets up to a basis. You can break spanning sets down to a basis. And this is kind of nice just because every once in a while you have a couple of particular vectors you want to be in your basis. And it's like, well, I got 2 vectors I want and I'm in a 4-dimensional space. Can I find a basis that has those 2 in it? It's like, yes, you can. You can build those 2 vectors up to be a basis by finding 2 more things to plug in there. So that's just an application of the plus-minus theorem. And then one last theorem here. If W is a subspace of a finite dimensional vector space V, then W is also finite dimensional. And the dimension of W is less than or equal to the dimension of V. And the dimension of W is equal to the dimension of V if and only if the 2 things are equal to each other. Okay. The textbook gives proofs of 2 and 3, and they leave the first one as an exercise. So I'll talk my way through a proof of the W is finite dimensional. So if W is a subspace of a finite dimensional vector space, so W might just be the 0 subspace, having just the 0 vector in it. Well, that we know is finite dimensional. It's dimension 0. Now, if it's not the 0-dimensional subspace, then it has a non-zero vector in it. Okay, that non-zero vector by itself is linearly independent. And so I'm going to use the theorem just before here that says if I've got a set that's linearly independent, I can build it up to a basis. Okay? That is, I can keep adding things, adding vectors to it, keeping independence but increasing the span. Now eventually I'm going to get up to as many vectors as, well, I'm going to get to the point of spanning W. If it's like, how do I know I'm going to get there? Well, I'm going to have to get to the point of spanning V because V is finite dimensional, and anything that's happening inside of W is happening inside of V. So if I've got a list of vectors that are all independent of each other, and I'm still not spanning W, you add another one, eventually you'll be spanning V because V is finite dimensional. So there's a finite list of things. I'm not going to, if it's 7-dimensional, this list that I'm creating can't have more than 7 in it because then that wouldn't be linearly independent anymore because V can only have 7 things, right? That is, eventually you'll be limited by the dimension of V as to how many things you can keep adding to that list, that growing list of vectors trying to make a basis for W. Okay, so it has to be finite dimensional. There has to be a finite set of vectors that spans W. Okay. So there you go. There's a bunch of theorems that give us some more insight into the workings of dimension and how do you prove that you have a basis if you know the dimension, right?